that leads us into our local extreme point theorem that states that if f has a local maximum or minimum value at c and f prime of c exists, then f prime of c must equal 0. All right, and we're going to actually use the reverse of this, and not that theorems are reversible, but we're going to use the reverse of this to help us find and identify local extrema, in that when our slope is equal to 0, that's when we're going to have local extrema. And these points, we call them critical points, and we say a critical point is an interior point C of the domain of f at which f prime of c is equal to 0, or when f prime of c fails to exist, and that's called a critical point. And that's where we're going to see these local extrema pop up. One thing to mention here though, just because a point is a critical point, that does not mean that it is a max or a min. It means it could be a max or a min. So if it's a max or min, it has to be a critical point. But just because it's a critical point doesn't mean that it's going to be either a maximum or minimum, whether relative or absolute. Let's look at this example to illustrate what I'm talking about here. In this function, y equals f of x, there is a point here at c where our slope is equal to 0. However, so we would call that a critical point, that c is a critical point. However, that is not a max or a min, neither local nor absolute. It's just a critical point that is something else that we're going to talk about in a little bit, but it's not a max or a min. So this is where we would see that our derivative is equal to 0 here. However, it is not one of our extrema. Another example is a vertical tangent line here, this function y equals f of x. So f prime of c does not exist. Therefore, c is a critical point once again, but also it is not a max or min. It's just another point where we are undefined, but it doesn't mean that we are going to be a max or min necessarily. It is a critical point, just not one that leads to a maximum or a minimum. So our procedure for locating absolute extreme values on a closed interval is we have to assume the function is continuous on the closed interval, and if we know that it's not, then we can't do these following steps. All right, so if the function is continuous on the interval, then we can do this. We need to locate any critical points C on the interval A to B, so just the stuff inside, and so that's where f of c is going to equal 0 or f of c does not exist. These are candidates for absolute maxima and minima, but they're not necessarily going to be those extrema. They're just possibilities. So we evaluate, once we have those points, we evaluate f at the critical points and at the endpoints. It's important to use the endpoints. Choose the largest and smallest values of f from the evaluation step, and that is going to be your absolute maximum and minimum values. If the interval of interest is an open interval, then the absolute extreme values, if they exist, occur at interior points. Let's take a look at a function. Say we have f of x is equal to x to the fourth minus 2x cubed, and we want to look on the interval -2 to 2. Okay, so let's find the critical points, and those critical points are going to be where f prime of x is equal to 0. Well, f prime of x, we need to take the derivative here. It gives us 4x cubed minus 6x squared. So let's set that equal to 0. In order to solve, we have to factor. Let's factor out a 2x squared, and then we get a 2x minus 3 is equal to 0. Well, this is true when x equals 0 and when x equals 3/2. So these are our two critical points. Those are the possible candidates for our absolute max or the absolute min. That doesn't mean it's going to happen there, but those are possibilities. What are the other two possibilities? Well, the other two possibilities are our endpoints. So we need to evaluate f of negative 2, f of 2, f of 0, and f of 3 halves. F of negative 2, when we put negative 2 back into f, we get 32. When we put 0 back into f, we get 0, because every term has an x. When we put 3 halves back into f, we get a negative 27/16. And when we put 2 back into f, we get 0. Okay, so that tells us that we have an absolute max at x equal to negative 2 of 32. And that's how I want you to say it, and you'll have to actually write that. The function f has an absolute max at x equal to negative 2 of 32. Or you could say the function f has an absolute max of 32 at the point where x equals negative 2. And the function f has a minimum of negative 27/16 at the value where x equals 3 halves. One thing I will mention, we did skip this earlier because it was a polynomial, but when we've set our derivative equal to 0 and find the critical points, we also have to ask, is our function, or is our derivative function ever undefined? And I didn't even mention it because with a polynomial the derivative will be defined. However, there will be functions sometimes that the derivative is undefined, and those are also going to be critical points. So points at which our function is undefined will also give us critical points. And if we look at the graph, we can see that it confirms that we have a absolute max at negative 32, and we have an absolute minimum at negative 27/16 at 3 halves. But we also notice that at the point 0, 0, that's not a local extrema. It is actually just a point where our slope is equal to 0, but it's neither a relative max or min. Before coming into class, I want you to give one a try. I want you to look at the function g of x is equal to x to the 2/3 times the quantity of 2 minus x on the interval of negative 1 to 2. I want you to find what is the absolute maximum and absolute minimum. In trying this, make sure you remember that when you set the derivative equal to 0, those will give you critical points, as well as when your derivative is undefined.